Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 11.3 from your textbook, and we're going to begin our investigation of how this new concept of a series relates to an older concept that we studied back in chapter 7, which was the improper integral. So to do this, we're going to introduce sort of our second major test for diagnosing the convergence or divergence of a series. If you remember back from 11.2, in 11.2 we sort of introduced two sort of types of series, geometric series and telescoping series, and we introduced one major test for series, which was what we called the test for divergence. Here in 11.3, we're going to introduce what is called the integral test. And the integral test is similar to the test for divergence in that it sort of tries to determine the behavior of an infinite series. And it's important from a theoretical standpoint because it connects what we're doing with series back to what we had already done with improper integrals. So let's go ahead, talk about what this integral test states. We're going to go through and talk about a bit of a proof for this integral test, and then we're going to look at a couple examples of it. So the integral test. So we're going to first suppose that you have a series, again, starts from some arbitrary spot, so n equals b. Again, starting spot really isn't going to matter. Runs to infinity, and you have that a sub n, which are the sequence values. So you're summing up that sequence. So we're going to suppose that you can find a function f of x that has three properties: continuous, decreasing, and always positive, on whatever sort of starting from wherever you're interested in starting your series from. Now, continuous, decreasing, and always positive, that's three very specific conditions. The continuous one is not much of a condition because obviously to just be a sort of a normal sort of function, we want it to be continuous. We're going to talk about the integral in just a moment, so this is not a particularly strong condition. But these two you really need to make sure. You have to make sure your function is always positive. Notice that that means that this will only work if your series elements, so those elements of the sequence, are also always positive, so that the function can be always positive, and decreasing, which we'll see is often the condition we have to actually check. We're going to further suppose that the function at each value of n is equal to the sequence. You guys have actually already seen a condition like this. This is what we used when we were back talking about sequences, and we used the replacement theorem. Remember, the replacement theorem was our technique for allowing ourselves to use something like L'Hopital's rule when analyzing a sequence, because the idea was if we could find a function that mimics the sequence at all the discrete values, then the limit of the function would be the same as the limit of the sequence. Here, we're doing sort of a similar idea, and we're trying to find a function that matches our sequence at all discrete values. Then, if all of these things are true, so if you can find this function, if the function is continuous, decreasing, and always positive, and the function matches the sequence for all n, then these statements hold. That says that if the sum or the series converges if and only if the improper integral converges, and the series diverges if and only if the improper integral diverges. In other words, you could summarize these and say that the series and improper integral have the same behavior. So this shows us that, in other words, if the series converges, then the improper integral converges. If the improper integral converges, then the series converges. If the series diverges, then the improper integral diverges. The improper integral diverges, the series diverges. So, in other words, the series and the improper integral will have the same behavior. Now, the reason it's so important to sort of mention same behavior is, as we will see as we start to sort of go through examples and also as we go through the proof, in the first situation, where the series converges and the improper integral converges, that means each of these actually approach finite values. When we say that one will converge, the other converges, that does not mean that the values will be equal. In other words, it's only the behavior that's the same. What this converges to will be different than what this converges to. So notice we're not saying that they equal each other. We're just saying that they have the same behavior. They either both converge or they both diverge. So let's go ahead and take a look at a quick proof. This proof sort of brings together a lot of concepts that we've covered so far, so it's, I think, a good one to sort of take a look at. So what we're going to do is we're going to first just try to draw out a picture to understand what why all these conditions are sort of used here. So we're going to start with a sort of visualization. So let's give ourselves an axis there. Okay, and just as a sort of note, we're just going to let, this is technically what is called without loss of generality. It's going to be an extra assumption that isn't going to impact anything. We're just going to assume that we're starting from like b equals 1. So instead of having, we've run a lot of our series from n equals 1. Again, starting spot doesn't matter. So we're just going to make it a little easier. Instead of having to carry the b around the entire time, we'll just say b is going to be 1. So we're going to imagine that we're sort of starting from 1. And then we have our sort of discrete values, and maybe there is our function. So that's my f of x. How do I know that I can draw it like that? Well, notice that it is continuous. It's always positive because it's above the x-axis, and of course it is decreasing. All right, now in a different color, here, each of those discrete values, right? That's your a sub n's, right? Each of those are your discrete values of your sequence, and of course your function matches them at all those discrete moments. In between, the function also continues on. Of course, the sequence does not, because the sequence is only defined at those discrete values. Okay, so what I'd like to do is I'd like to visualize this as some areas here. So let's go ahead, and we're just going to sort of put a dotted line there. So we're going to take a look at sort of this blue area under our function. Now, that blue area, you should be easily convinced that that blue area, of course, is an integral. It's the integral under this function from 1 onwards. So this would be the integral from 1 to infinity, f of x dx. Right, so the blue area, that's the area under the curve. Now, what if we sort of did a rectangular approximation using these values here? Well, if I make some rectangles, and I'm going to do a left endpoint approximation. So there we go. So on and so forth. Now, first thing you should be convinced about is that the red area, so the area inside those red rectangles, well, notice that because the function is strictly decreasing, and since I did a left endpoint approximation, every one of those red rectangles is an overestimate. So you should definitely be convinced that the red area is going to be greater than the blue area. That should be definitely clear from our visualization here. Okay, but what can we say about the red area? Well, each of these, because we said these are discrete values, each of these are with 1. Right? That's 1, that's 1, that's 1. And of course, the height of each of these is the function. So we can actually talk a little bit about the red area. The red area is actually equal to, well, the height is f at x, at f at 1, not x1, we can just say 1, because we know we started at 1, plus f of 2, plus f of 3, plus dot, 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 right? Because there's the function at 1, and there's the function at 2, there's the function at 3, right? So that gets each of those rectangles. And of course, hidden in here, they're each times 1, which is the size of the base, right? So height times base there. Okay, but remember, our function matches our sequence at every value. So this red area is actually equal to a1 plus a2 plus a3 plus dot, dot, dot. So notice then that we could actually say that the red area, there we go, the red area is actually equal to the sum from n equals 1 to infinity of a sub n. So in other words, the red area matches the size of our series. So what we've just established is putting this together. We have this relation. We have that the sum from n equals 1 to infinity of a sub n must be greater than the integral from 1 to infinity f of x dx. So we've just established that the sum of our series must be larger than the improper integral. Okay, let's grab this and talk about what we can sort of grab, or what we can sort of deduce from this. So let's give ourselves another sort of page here. Okay, so we've just determined this. So let's go ahead and, for right now, let's assume that the integral from 1 to infinity f of x dx diverges. So let's assume that this improper integral diverges. What does that tell us? Well, if we look back, since the function is always positive, we know that if it diverges, this stuff in here must be going towards positive infinity. In other words, it must have a positively infinite area. So if that's the case, then since f of x strictly decreasing plus always positive, that tells us that the integral 1 to infinity f of x dx is actually headed towards positive infinity. Okay, but if this is headed towards positive infinity and this is larger, well, then this sum from n equals 1 to infinity, a sub n, must also be headed to positive infinity because it's supposed to be larger than this, which implies this sum n equals 1 to infinity, a sub n, diverges. Check. Okay, so what have we actually done here? Well, in some ways, we are a quarter done with our proof, because what we've just shown, if we go back to our 4 statements here, we've just shown that if this diverges, then this diverges. We've got 3 more things to sort of prove. We need to show that if this diverges, then this diverges. We need to show if this converges, then this converges. And if this converges, this converges. But we've done one of the 4 pieces. We've shown that if this diverges, we automatically know this diverges. So, is it going to sort of only be 1/4 of the work? Well, no. We actually get another one very easily. If we look back at this inequality, we sort of assume that this diverged, and then we said that this was bigger than something that diverged, so it diverged. Now, let's go ahead and assume that this converges, so that we have that this is smaller than something that converges. So now, let's go ahead and assume that the sum from n equals 1 to infinity, a sub n, converges. Then, what we know is then the integral from 1 to infinity f of x dx must be less. So remember, if this converges, then this is actually going to some number, and our improper integral has to be less than that number. So the improper integral is less than some number. So what that means is that the limit as t goes to infinity of the integral from 1 to t f of x dx is less than some number. So the limit is bounded. Okay? So we know that there's an upper bound to this limit. But we also know something else. Since f of x is always positive, this limit is always increasing. Right? As t goes further, right, since f of x is always positive, we're always adding a little bit more positive area. So we know that this limit is always increasing and it's bounded. Well, you have that monotonic convergence theorem. So by the MCT, limit t goes to infinity, integral 1 to t f of x dx must converge. Remember that monotonic convergence theorem says that if something is bounded and monotonic, in this case bounded and increasing, then it converges. So what we've just shown is that if we assume that the sum converges, then the improper integral converges. So what this tells us then is that we've gone back and we've shown this direction. If this guy converges, then this converges. So at this point, we can say we're sort of half done. So that we can say we're at the halfway point. We have proved that if the integral from 1 to infinity f of x dx diverges, then this implies that the sum diverges. So we did that, and then what we just did is we just showed that if the sum converges, then this implies that the improper integral converges. Okay, so that is 2 of the 4 statements. All right, to get the other 2, we're going to do a very similar approach, but we're just going to change our visualization. So let's go ahead and look at our visualization again. So same idea. There's my curve like that, and we're again looking at just those discrete moments. And again, I'm going to label those discrete moments in green. And so remember, black is our f of x, the green is our a sub n. And once again, let's look at the area here. Okay, this time though, what I'm going to do, instead of doing a left end approximation, I'm going to do a right end approximation. So I'm going to draw here, and I'm going to draw some rectangles. Oh, I think I did this in red last time, so let's stay consistent. So I'm going to draw some left end approximations. Okay, and I apologize that my first one is a lot skinnier. They all should be with 1, of course. Okay, now it should be very easy to see here that the blue area this time is going to be greater than the red area. And that tells us that the improper integral from 1 to infinity f of x dx is going to be greater than whatever that red area is. So this time, since we did a right end approximation, all of the red rectangles are underestimates, so the red area is smaller than the improper integral. Okay, what can we say about that red area, though? Well, the red area, if we look at it, is, well, we use this guy here, this one, first. So it would actually be something like a2 plus a3 plus dot, dot, dot. It doesn't have a1 because we didn't use this one, but it started from 2, 3, 4, etc. So if we think about that, we could say that the red area is actually the sum from n equals 2 to infinity of a sub n. And since, that doesn't quite start where we wanted it to, notice we could just sort of dumbly think about the red area as the sum from n equals 1 to infinity of a sub n minus a sub 1. So in other words, it's our infinite series minus the first term. Okay, so now we've established that the integral from 1 to infinity f of x dx must be larger than our sum from n equals 1 to infinity a sub n minus a sub 1. So our series minus a finite value. Okay, so notice that this is very similar, but sort of the reverse direction of this statement. Okay, so now we should be able to get these other 2 statements. Remember, we used that first inequality to get the first 2 statements. Now we can use this to get the other 2. And the logic is going to be very similar. So let's grab that. And we'll bring this onto our last page here. Okay, so let's see what we can do with this. So let's go ahead and assume that the sum from n equals 1 to infinity, a sub n, diverges. Well, once again, that means it's going to be headed towards positive infinity. How do we know that? I mean, remember, in general, diverges could mean positive infinity, negative infinity, or does not exist. But remember, each of these a sub n's is a positive number, so if you just keep adding up positive numbers and that diverges, well, that must mean that it's going to positive infinity. So we know that this is headed towards positive infinity. Subtracting a finite value, that's not going to change anything. So that means a sub n minus a sub 1. This is just a single value. That's also headed to positive infinity. So our improper integral is greater than positive infinity. So that tells us that the integral from 1 to infinity f of x dx must also diverge. Okay. So that's another one of the directions. If we go back, Now we've shown that if this diverges, then this one diverges. Okay, last thing we need to do, right, is prove the fourth direction. Remember that the last one we need to do is that if this converges, then this converges. Okay, so let's see if we can do that. So now let's go ahead and assume the integral from 1 to infinity f of x dx converges. So in other words, it goes to some number. Well, notice then that that tells us that we have some number is less, or is greater, excuse me, than our series minus a sub 1. If you bring this a sub 1 over, then you'd have some number plus a sub 1 is greater than the sum from n equals 1 to infinity of a sub n. Now, this is some number plus a sub 1. This is still, over here, just a number, right? It's still just a number because it's a number plus another number. I mean, it's still a finite value. So we know that the sum from n equals 1 to infinity of a sub n is bounded above. So we know that it's bounded above, and since it's a sum of positive terms, it is strictly increasing. If you keep adding more and more positive numbers, you know you have something that is strictly increasing. So we know that it's bounded above and strictly increasing. We can use that monotonic convergence theorem. So by MCT, that sum from n equals 1 to infinity a sub n converges. So we've shown that if we assume that the improper integral converges, then the series converges. So putting all that together, we have all four statements now. We now know that if the series converges, the improper integral converges. If the series diverges, the improper integral diverges. If the improper integral converges, the series converges. If the improper integral diverges, the series diverges. Notice also along the way, we showed why I made this special mention of same behavior rather than being equal. Along the way, we actually showed right here that the infinite series, if it is a finite number, will be a larger finite number than the improper integral. So again, remember, this is not saying that they are equal. It's saying that they have the same behavior. Okay, let's go ahead then and take a look, since this was a pretty lengthy proof, of actually using this sort of theorem to actually analyze the behavior of some series. So let's get into our first example. So we're going to determine if the following series converges or diverges. If you look at this, this is n equals 1 to infinity of 1 over n. This is a very sort of important series. It's often called the harmonic series. We actually talked about this series back in 11.2 when we sort of just gave some examples of series. Remember, this is the one that goes 1 plus a half plus a third plus a fourth. And we said that this is a very interesting question because these things are definitely headed to 0, but you're summing them up. This was one of those ones that's actually worth analyzing because you're really summing up an infinite amount of infinitesimally small things. We actually didn't have the mechanisms to analyze this back in 11.2 because it's non-geometric and it's non-telescoping, but now that we have this integral test, we can actually analyze this. So what is the sort of corresponding function here? Well, we're going to consider f of x equal to 1 over x on the interval from 1 to infinity. So let's think about this. Is this continuous? Well, 1 over x has some issues near 0, because then you'd have a divide by 0, but we're on 1 to infinity, so it's all good. Is it positive? Well, 1 divided by anything from 1 to infinity is going to be positive, so it's good. And is it decreasing? Remember, those are the three conditions. Well, we could, to show decreasing, like take its derivative and show that it's negative, but that's way overkill here. Remember, this is a number, that's just 1, over something that gets larger and larger as we go on. So this is a number over something that gets larger, which means that it's automatically decreasing. So this fits the three conditions of our integral test. So now we can use integral test. So for integral test, we're going to consider now the integral from 1 to infinity of 1 over x dx. So we're translating from a series where, to be honest, we don't know much about how to analyze series yet, right? We've said basically we know how to analyze geometric, we know how to analyze telescoping, and we have that test for divergence. But notice that if we try the test for divergence here, the limit as n goes to infinity of 1 over n is 0, which means there's no information. The test for divergence only tells us if this limit is non-zero, then we know that it diverges. But we know quite a bit about analyzing improper integrals. We know that we can rephrase this as a limit as t goes to infinity of 1 over t, or 1 to t, 1 over x dx. Then we know that this we can actually go ahead and get the antiderivative of. So we have ln absolute value x evaluated from 1 to t. And then we have the limit as t goes to infinity, ln of t minus ln of 1, dropping the absolute value bars because we know we're working on 1 to infinity where everything's positive. This, of course, is 0, and this, well, as t goes to infinity, this heads to positive infinity. So what we know is that the integral from 1 to infinity, 1 over x dx, diverges. Okay, so the improper integral converges. Considering that all the conditions were met, that means that the infinite series diverges. So, by integral test, sum n equals 1 to infinity, 1 over n also diverges. That's exactly what integral test says. It says that if those three conditions of four conditions, I guess, the function matching the sequence, being continuous, positive, and strictly decreasing, then the behavior of the improper integral is the same as the behavior of the series. So we know that this also diverges. Now, if you really think back to when we studied improper integrals in a lot of depth in 7.8, you could actually say that we could have probably skipped this antiderivative. Once we got to right here, once we had this as an improper integral, remember this we had something called the p-test for, because this was the improper integral from 1 to infinity of 1 over x to the p dx. And we said that those things diverge when p is less than or equal to 1, and they converge when p is greater than 1. So we could have actually just said, oh, right as soon as we got here, use the p-test, it's going to diverge because the power is 1, which is less than or equal to 1. So we could have just jumped right to here. And in fact, that jump there, that tells you that there's a strong connection between the p-test and a type of series. So we're going to talk about that before we get into our next set of examples. So a series of the form 1 over n to the p is called a p-series, sort of in the same language as that p-test. These types of series will converge when p is greater than 1, and they will diverge for p less than or equal to 1. This is exactly mimicking the p-test for improper integrals. And the explanation is that something of this form, n equals 1 to infinity, 1 over n to p, you can always, let's use a nicer sort of phrasing there, for any sort of sum like this, you can use integral test with 1 over x to the p, with our function being 1 over x to the p. Then, by p-test, which is what we sort of called it for improper integrals, the integral from 1 to infinity, 1 over x to the p dx, is going to converge if p is greater than 1, diverge if p is less than or equal to 1. And since the integral test tells us that the series has the same behavior, and notice that 1 over x to the p is going to be continuous, it's going to be strictly positive, and it's going to be strictly decreasing. So the integral test is always going to imply, so these p series have the same behavior here. So now, with the integral test, not only have we introduced this new test, but we also have a new type of series, just like geometrics, where we actually understand their behavior. When do they converge? When do they diverge? The thing I'd like you guys to consider, though, here is that unlike geometric series, the p-series, we know when they converge and when they diverge, but we do not have a closed formula for what they converge to. For geometric series, we know when they converge, when they diverge, and what they converge to. In other words, the sum of the actual series. For p-series, we have more limited information. We know when they converge, we know when they diverge, but we do not know, in the situation when they converge, what they actually sum up to. We're going to revisit p-series a lot more in the next section because we're going to be doing what are called comparison tests, and p-series are often what we compare against. So this definition here is going to be very important as we move on. These p-series, these are a very common type of series. For now, though, I'd like to wrap up this video by looking at a couple more examples of just running the integral test directly. So let's jump into those. So we're going to try to determine if this series here converges or diverges. Okay. First thing is, as you were working with series, you should always think about that test for divergence. Now, of course, we're in the integral test section here, meaning that the test for divergence is probably not going to yield any information, but let's just go ahead and try it. So that test for divergence, we would take the limit as n goes to infinity of a sub n, which would be the limit as n goes to infinity of 1 over n ln n. Notice that that's going to go to infinity, that is going to go to infinity, so this is going to go to 0. So these terms do go to 0. So in the long run, we are summing up an infinite amount of infinitesimally small things. That, unfortunately, is the indeterminate form. That's when we actually have to analyze. So this test for divergence gave us no info. If this had come out as 1 or 2 or infinity or does not exist, then we'd just be immediately done and we'd say this series diverges. But unfortunately, when you get a limit of 0, that is no information. So could we just say that this is a p-series? Well, unfortunately, the p-series is 1 over n to a power. It has nothing to do with that ln of n, so we can't just say that this is a p-series. Unfortunately, it's also non-geometric, right, because it's not some number to the n. So we're going to have to analyze it through integral test. So what we're going to do is we're going to consider f of x to be, oh, and I just caught a little typo here. Let's imagine that that runs from 2. Otherwise, we'd have something that's undefined at n equals 1. Again, it doesn't really matter, but we should have n equals 2 there just to be consistent. Let's consider x ln x on 2 to infinity. Well, is this thing continuous? Well, for sure, right? As long as we stay away from where those things are 0, it's going to be continuous. Check. Is it positive? Well, again, as soon as we start putting in positive numbers in here, of course, x is going to be positive, and ln x is positive once you're past 1, so it is going to be positive. Is it going to be decreasing? Well, it is a number over a denominator that gets larger and larger, which means that it is going to get smaller and smaller. So it has all 3 conditions. So we can go ahead and look at this as the integral from 1 to infinity, 1 over x ln x dx. Now that is an improper integral, so we're going to immediately change it into a limit with our dummy variable. So we have that there. Then we're going to go ahead and actually figure out how to integrate this. It might be a little bit messy, but notice that we could u sub for that ln x. So let's let u equal ln x, and the du is 1 over x dx, which is exactly what we have there. We should change our bounds. Our original bounds in x are t and 1. In u, it's going to be ln of t and ln of 1, because u equals ln x. And of course, that means the new lower bound is going to be 0. So that means we have the limit as t goes to infinity, the integral from 0 to ln of t, 1 over. And if we look in here, oh, and I'm sorry, I still have that same typo. I don't know what I'm thinking there. These should all be 2's because we're running this from 2. And that means that this thing here should be 2. And that's going to be ln of 2. My apologies on that. So, wouldn't be well defined if we started it from 1. Okay, ln of 2. All right. And like we said, the 1 over x dx is going to be used up as our du. So we're just going to end up with 1 over u du. Now let's go ahead and integrate that. We get the limit as t goes to infinity, ln absolute value u, evaluated from ln of 2 to ln of t. So we get the limit as t goes to infinity, ln of t minus ln of 2. Okay, again, that's just some nasty sort of number there. Here, as t goes to infinity, this part is going to go to positive infinity, and then ln of positive infinity is still going to tend towards positive infinity. Now, ln of ln moves very slowly. You can put in massive numbers, and they're still pretty small, but it does keep increasing. So the main point is that this goes to positive infinity. So that tells us that the integral, again, 2 to infinity, 1 over x ln x dx diverges. So the improper integral diverges. Since we confirmed all these conditions and our function matches our series, well, we can say by integral test, the sum from n equals 2 to infinity, 1 over n ln n, also diverges. So we know that this series also diverges. So again, second example of running the integral test, right? We weren't able to analyze this any other way. Test for divergence gave us no information. This was not a geometric. It was not telescoping. It's not a p-series, but we were able to analyze it by considering the corresponding improper integral, and we figured out that it was divergent. Okay, let's take a look at another one. We're going to try to determine if this series converges or diverges. Well, we've got from n equals 2 to infinity, 2n over e to the n. If you wanted to, you could try that test for divergence to start with. Take the limit as n goes to infinity, 2n over e to the n. This is an infinity over infinity case, so you might want to use like a replacement theorem and get the limit as x goes to infinity, 2x over e to the x. Then apply a L'Hopital and get limit x goes to infinity, 2 over e to the x, which equals 0. So, unfortunately, that means we get no info from our test for divergence. No information here. All right, so now we're going to try the integral test. So let's consider f of x equals 2x over e to the x. Or if you prefer, 2xe to the negative x. And of course, we're going to be doing that on 2 to infinity. Well, is that thing continuous? For sure, right? This is a product, and e to the negative x doesn't have any issue, so this is definitely going to be continuous. Is it positive? Well, no matter what I put in here, this is positive, and e is always positive, so we're good. Is it decreasing? Well, that's much harder to see here, because in this form, you can't really tell. And here, well, you can't say that it's a number over something that gets larger, because both 2x and e to the x gets larger. So to do this, we're going to need to consider the derivative. Remember, being decreasing just means that your derivative is negative. So unfortunately, since this is a slightly more complicated function, we got to consider the derivative. Let's look at maybe taking derivative here. We could do this, but then we'd use quotient rule. So I'd prefer to use product rule. Should be 2e to the minus x, and then minus 2xe to the minus x. Or if you rewrite that, it looks like it's 2 minus 2x e to the negative x. Well, we know that this portion here is always going to be positive, and if x is from 2 to infinity, this is always going to be negative. So you have a negative times a positive, which means that this is always going to be less than 0. So the derivative is always less than 0. That does mean that it is decreasing. Check. So it's continuous, positive, and decreasing. We can go ahead and use our integral test. So we're now going to consider the integral from 2 to infinity. We have 2x e to the minus x dx. Since that's an improper integral, we immediately want to change it into a limit. There we go. How do we analyze this sort of antiderivative? Well, it's a product, so we can use something like integration by parts. So let's let the u be 2x and the dv be e to the negative x dx. du will be 2 dx then, and v will be negative e to the negative x. So we get the limit as t goes to infinity. And in here, we have our uv, so negative 2x e to the negative x, minus the integral of our v du, so minus 2e to the negative x dx. And all that is evaluated from 2 to t. We can go ahead and finish this up. The negatives are going to cancel, but we're going to get another negative when we integrate. So we get the limit as t goes to infinity, negative 2x e to the negative x, minus 2e to the negative x, evaluated from 2 to t. Then we can go ahead and pull this up here and plug in, so we get the limit as t goes to infinity, and we have minus 2t e to the minus t, minus 2e to the minus t. And then we got to plug in our 2, so we have minus, and then parentheses looks like minus 4e to the minus 2, minus 2e to the minus 2. Okay, so that's a little bit messy, but let's just take a look at what we have. We have the limit as t goes to infinity, and since we're going to be doing limits, it might be useful now to rewrite those e to the negative t's in the denominator. So we have minus 2t over e to the t, minus 2 over e to the t, and then I guess plus 6e to the negative 2. Okay, well, this limit only applies to these two terms. This term here, we clearly know that that's going to go to 0. How do we know that? Well, it's a number over something that's going to go larger and larger. That e to the t is going to go to infinity, so this is going to go to 0. What about this? Well, technically, this is infinity over infinity. And this is going to get larger and larger. This is going to get larger and larger. But notice we actually analyze that limit right back up here, right? 2t over e to the t, that's the same as like 2x over e to the x. We actually know it's going to go to 0 as well. So we can use our little previous work. This here goes to 0 by the above. So those terms are going to go to 0. So this is going to give us 6e to the negative 2. So that tells us that the improper integral from 2 to infinity of that 2x e to the negative x dx converges to 6e to the negative 2. So the area under this curve from 2 to infinity is equivalent to the finite number 6e to the negative 2. Does that mean that the improper integral, that the series is equal to 6e to the negative 2? No. But it does mean that by integral test, it converges. So we can say by integral test, sum n equals 2 to infinity, 2n over e to the n also converges. But notice we are unable to say what this converges to. In fact, by our proof of integral test, we only know that this thing is larger than 6e to the negative 2. So we know that this is a finite number and larger than that. But that's it. Okay, so this one was a little bit messier because we actually had to confirm that the function was decreasing, and we actually had to use an integration technique in analyzing the antiderivative. This is why, in the long run, integral test is not going to be one of our favorite techniques because, again, showing that something is decreasing might be pretty challenging, and it might not always be true. And we know that taking antiderivatives can also be quite challenging and sometimes impossible. So integral test is really important theoretically in terms of establishing this link between the series and the improper integral. But computationally, it's not going to be one of our ideal techniques because, again, it's got a lot of confirmation you need to do at the beginning and a lot of work in terms of actually determining the behavior. All right, let's take a look at one final example. So we're going to determine if this series converges or diverges. Now, you might say, okay, let's jump right into integral test. But let's go ahead and really quickly try that test for divergence. So we need to take the limit as n goes to infinity of this here. Notice that this is sort of like one of those polynomial ones. I mean, it's got that radical there, but we can multiply top and bottom by 1 over n. And up top, we would get 1. And in here, well, 1 over n is the same as the square root of 1 over n squared. So if we pull that inside, we'd get 1 minus 1 over n squared. Notice that that's going to go to 0. So we're going to get 1 over 1, which is equal to 1. So as a sequence, this converges to 1. So in the long run, this is adding up an infinite amount of 1s. So this is not equal to 0. So by test for divergence, this diverges. So we don't have anything else we need to do. No need to do an integral test here. We know that this thing diverges. If you want, you can try an integral test yourself with f of x equals x over the square root of x squared minus 1. You'll need to use the derivative to show that it's decreasing. And when you do your integration, you'll need to use a u substitution to actually integrate it. It will work, and you will find that it diverges. But notice that the test for divergence does it much faster, because this isn't even an interesting series. This, in the long run, is just adding up an infinite amount of 1s. We immediately know that it diverges. This wraps up section 11.3 for us. In our next video, we'll be moving into 11.4, which really introduces us to one of the most powerful ways of analyzing the behavior of series, which are the comparison tests.